Hello. Yeah. Can you hear me? So welcome to the opening section of concurrency, and we have many exciting talks and some brief announcement. And let me remind you that the full paper presentation is for 5 minutes, and for the brief announcement is for 3 more minutes. And please ask your question in the Zoom chat, and that's about it. So the first talk is by Sahil from University of Texas at Dallas, and it's actually a best student paper. It's called An Adaptive Approach to Recoverable Mutual Exclusion. Sahil, please share your screen. I will unmute you.
Hello.
Hello? Yes,
yeah.
I can hear you. Please go ahead. Thank you.
Hello, everyone. Today, I, Sahil Dhokad, and with my advisor, Dr. Neeraj Mittal, are going to present a small overview of our work on an adaptive approach to recoverable mutual exclusion. We represent the Andes lab at UTD. So with that, let's get started. Let me present a small introduction. The problem of mutual exclusion is to allow processes to execute a part of their code, which is known as critical section, in isolation. This helps us avoid race conditions and keeps the system consistent. Traditionally, mutual exclusion algorithms are not designed to account for failures, especially in shared memory systems. However, failures can occur in the real world. At any time, there could be a power outage or any segmentation fault, leaving the system in an inconsistent state. With new technology, as NVRAMs, like our keynote speaker presented today, we can handle failures very effectively. NVRAMs combine the low latency of our traditional RAMs along with the persistence of our hard disk. This helps us get near instantaneous recovery from failures, which gives rise to the problem of recoverable mutual exclusion. Now we'll present a small summary of our contributions to recoverable mutual exclusion. We have presented a new solution, which we like to call as the strongly recoverable mutual exclusion problem. Our solution is adaptive. It is bounded. The RMR complexity is given by minimum of square root of f and log n by log n, where f is the number of recent failures in the system. Our algorithm can also be used to transform any existing or new solutions to make them bounded and adaptive. Our algorithm satisfies first come, first serve in the absence of recent failures. And the next 2 points are not there in our PODC conference, but we are able to achieve these two. Our algorithm is able to handle batch failures adaptively and is also able to do memory reclamation. So the key ideas in our solution is we define a new problem called as the weakly recoverable mutual exclusion problem and provide an optimal solution to it. And using that, we create a framework which acts as a transformation framework, and we recursively use this transformation framework. We have identified 3 scenarios where we like to compute the RMR complexity in the absence of failures, in the presence of F failures, and in the presence of a large number of failures. And our algorithm provides the following RMR complexity: a constant, square root of F, and log n by log n respectively for these 3 cases. And now we present our solution to the recoverable mutual exclusion. We first define a new problem, which is the weakly recoverable mutual exclusion problem, or what we like to call weak recoverability. This forms a key component of our solution. The idea is to allow multiple processes in the critical section simultaneously for a small amount of time in the presence of recent failures, but there could be no compromise at the cost of starvation freedom. We extend the well-known MCS lock to provide an optimal solution to the weakly recoverable problem. Where the MCS lock creates a queue of requests using a fetch and store instruction. And in our algorithm, if there's a failure during the fetch and store instruction, a process simply aborts and retries. Where in doing so, multiple subqueues might be created in the system. For example, if there are 8 processes that do a fetch and store and P4 and P7 fail, then there are 3 subqueues created and there are 3 processes in the critical section simultaneously. That is why our lock is weakly recoverable. Using this weakly recoverable lock, we present our work as an adaptive transformation. So this framework that we present over here transforms any core lock to a semi-adaptive lock using other components as well. The requirement is that the core lock should be strongly recoverable, and using that, our framework also becomes strongly recoverable. So since our framework is strongly recoverable, we could substitute another instance of this framework in place of the core lock. And we keep doing this for till M levels to get an adaptive algorithm. Our algorithm, in fact, is super adaptive because it depends on, it's sublinear in the number of failures, and it satisfies all desirable properties. And if we use Jayanti and Joshi's lock for our algorithm, we get the following RMR complexity, and we can use other future solutions as well for the core lock. Now we'll present some extensions to our work that we were able to achieve after we submitted our conference version to paper of our conference paper. Memory reclamation, we use an idea similar to epoch-based memory reclamation with a space overhead of n square log n by log n and a constant RMR overhead. And in the presence of batch failures, we are able to get an RMR complexity of FB, minimum of FB plus square root of F and log n by log n, where FB is the number of recent batch failures and F is the number of recent individual failures. And system-wide failures is a special case of batch failures. So this was a small presentation of our work. If there are any questions, you could ask me now, or you could contact me later on Zulip.
All right, thank you, Sahil. I guess we have time for one question. Any questions? Otherwise, you can post. Okay, Cody, let me unmute you. Please go ahead.
Okay, so you said your algorithm is based on the MCS lock, and the MCS lock, the exit code is not weight free. What about your solution?
Yes, so there is an extension of the MCS lock that is weight free. I think there's a paper by you and Dvir, if I'm not wrong, and we use that version to achieve weight free exit.
Okay, cool. So yeah, please bring the other question to the Zoom session or like Zuzip, and we have to move to the next presenter. So it's Ohad from Ben Gurion, and the paper is called Upper and Lower Bounds on the Space Complexity for Detectable Objects. Ohad, please share your screen. I will unmute you now. Looks like we don't have the response from him. Maybe let's wait for, say, maybe a few seconds. Otherwise, maybe we should go ahead with another talk since we are very short on time.
I see Ohad.
Yeah, I just talked with him like maybe 10 minutes ago, but like. Let's see. Okay, Cody. I unmute you. Any suggestions or questions? Okay, maybe we should go to
So,
the
Louis,
next.
so
Hello?
yeah, so Louis, so I see Ohad's picture, but somehow I can't unmute him.
Yeah, I mean, he has to agree to be unmuted. Yeah, so I guess he's not in front of the, yeah.
I see
the
live
computer.
video of him. So
Oh, you see live video of
yes,
him?
yes, he's there.
Okay.
So yeah.
So maybe there's some technical issues. I suggest that we go to the next talk first and then maybe come back later. Would that be fine?
Sure.
Okay. So the next in line is by Matthew from LS2N. Yeah, the paper title is called Extending the Wave-Free Hierarchy to Multi-Thread Systems. Wait a minute, let me unmute you. All right, Matthew, I just unmute you. Please go ahead. It's all yours.
Thank you. So can you hear me?
Yes.
So this is a joint work with Ashram Mostefawi and Grégoire Bonin. The wave-free hierarchy was proposed by Hurley in order to compare the synchronization power of shared objects in crash-prone asynchronous systems. It is based on the notion of weight-free universality. So an object O is weight-free universal if any object that is weight-free and linearizable can be implemented using only read-write registers and instances of O. An object has consensus number K if it is weight-free universal in a system composed of K processes, but not in a system composed of K plus 1 processes. If such K does not exist, then we say that the object has consensus number infinite. In recent decades, parallelism in multi-core architectures has been abstracted by the notion of threads that can be created dynamically throughout an execution. So although at each time the number of threads is finite, there is no bound on the number of threads that can participate in a long-running execution. Another specificity must be taken into account in the fact that threads share a common memory from which they can allocate unbounded but finite numbers of memory locations. These two considerations have an impact on which algorithms can be implemented in multi-threaded systems and which algorithms cannot. For example, it is not trivial how to allocate one shared register to each thread, which is required by many weight-free algorithms. Indeed, an object that is called the iterator stack has been introduced by Affek, Morrison, and Wertheim that is not universal in multi-threaded systems, despite having an infinite consensus number. So the question I ask in this talk is how to compare the synchronization power of shared objects in multi-threaded systems. Following the same approach as earlier, we propose to compare the synchronization power of shared objects based on the number of processes that they are able to synchronize, including in situations where this number is unknown by the processes or may change during the execution. 4 arrival models were previously introduced that are composed of asynchronous processes that may arrive, leave, or crash during an execution. M1N is a classical model composed of N processes. M1 is a bounded arrival model where the bound is known to the processes, but it may change from one execution to another. M2 is the finite arrival model where processes stop arriving after some time. And M3 is the most general infinite arrival model that consists of, at each time, a finite number of threads, but there is no bound on the number of threads in an execution. We then propose a bidimensional hierarchy in which objects are sorted horizontally on their universality in models M1N, M1, M2, and M3 when no infinite memory allocation is available, and vertically on their universality in the same models enriched with an infinite memory allocation mechanism. We then explore for each new category whether there exists an object or not in this category. So for example, in the rightmost and bottommost triangle, this only contains empty categories, because if an algorithm does not require infinite memory allocation, then it still works when this is available. We proved last year at DISC that consensus is indeed still universal in multi-threaded systems. And we can also place the iterator stack as an object that is universal in M2, but not in M3. Objects with a finite consensus number lie in the leftmost column. So an important result of ours is that in models M1, N, and M1, it is actually not important to have infinite memory allocation when we consider universality. And that means our hierarchy coincides with the weight-free hierarchy for objects with a finite consensus number. This also justifies why we keep the same name consensus number to designate our degrees in our hierarchy. So an object has consensus number infinite x, y. If it is universal in model M x, but not in model M x plus 1 when infinite memory allocation is not available. And if it is universal in model M y, but not model M y plus 1 when infinite memory allocation is available. Finally, we prove that no object has consensus number infinite 1, 1, but that the 3 remaining categories have a representative, so that the set of objects with infinite number are divided into 5 new categories. Thank you for your attention, and I would be glad to answer your questions.
Thank you, Matthew. Any questions? We have time for one question. Okay, Matthew, did you see a comment from Fed? It's in the chat.
Sorry.
No problem. Yeah, it's a bit confusing.
Yeah, I'm not used to.
Okay, so maybe I'll just
consider. Yes,
yeah.
please.
So Faith said that it might be better to call what you do a classification rather than a hierarchy. Do you have any comments on that, thoughts?
So I think she says that because the classification or hierarchy is not strict. For example, objects with infinite 2, 2 consensus number are not comparable with objects with an infinite 1, 3 consensus number. So that is correct. It may be better to call it a classification. It does not change the scientific results yet.
Okay, and then she pointed out that a hierarchy is also a linear ordering. Yeah, I guess that's just comment.
Yes. However, we still can use it to compare the power of some objects. For example, consensus is strictly stronger than window registers, or the iterator stack as well is stronger than window registers. So there is still an order, even if it's not a linear order.
Okay. So yeah, if sounds good, and thanks for the talk. If you have more questions or more comments, please take it to the chat. And now let's move on to back to OHAB. Sorry, there was some technical issue. Yeah, thank you, Matthew. And that's OHAB. Please share your screen. Let's see that if we can get some more luck this time.
Hi, now you can hear me?
Yes, I can hear you now.
Okay.
That's good.
Yeah, sorry for the technical issues. Yeah, like a computer scientist, you simply need to restart. Okay, you can see my screen?
Yes, please go ahead.
Okay, so I will present the paper Upper and Lower Bounds on the Space Complexity of Detectable Objects. And this is a joint work with Danny Hender and Matan Rosanos. So just like the first talk, this work also is motivated by the introduction of new non-volatile RAM technologies. So in past days, in order to recover an object, a copy of which had to be stored in the secondary storage, which is very costly in terms of space and time, both for maintaining the copy and also for using it in order to recover. And NVRAMs allows in-memory object recovery to be accomplished much more quickly by directly fixing the persistent main memory state. So Israelevich et al. Presented the durable and usability correctness condition for the crash recovery model. After a crash, the state of the object must reflect an history containing all completed operation, but crashed operation may or may not be part of this history. However, in addition to recover the state of the object itself, we also would like to allow processes to recover and continue with their execution. And for that, upon recovery, a process needs to be able to conclude whether its crashed operation took effect and also to obtain its response. And this notion was defined by Friedman et al. As detectability. Each process runs a recovery procedure after a crash, which infers whether the crashed operation was linearized, and if so, also obtain its response. So in the last few years, several detectable implementations have been presented. Friedman et al. Presented a detectable queue. A detectable compare swap was developed independently by both Atiyah et al. And Ben David et al. And Atiyah et al. Also presented a detectable read-write register. All these detectable implementations share the fact that an unbounded sequence number is used, and therefore they all have an unbounded space complexity. And this raises the question, does unbounded space is inherent to detectable implementations? In addition to the fact that sequence numbers are used, those sequence numbers must be passed to the operation as an argument. So in other words, sequence numbers are not maintained by the operation itself as usual, but rather by the caller of the operation. And the only exception is the Atiyah et al. Compare and swap algorithm, but this algorithm makes the assumption that in case of a crash, the system provides the last instruction pointer. And this raises the question, does this kind of auxiliary state, namely some external information that is provided by either the caller or by the system, is necessary for detectable implementations? So in this work, we provide a negative answer for the first question, presenting the first bounded space detectable read-write register implementation. And we also present a bounded space detectable implementation for compare and swap. In addition, we prove that the space complexity of our compare and swap implementation is asymptotically optimal by presenting a matching lower bound of omega n share bits for any detectable compare and swap implementation. And finally, we prove that for a large class of objects, auxiliary state is indeed required for detectable implementations. And this class includes read-write register, compare and swap, queue, stack, and more. And we emphasize that this requirement is in order to support detectability. Therefore, recoverability by itself does not require auxiliary state. So to summarize some key points to take from this work, as we have shown, for many objects, any obstruction-free detectable implementation requires a model with auxiliary state that is either supplied by the calling process or by the system. We show in this paper how standard techniques such as handshake and vector bits that were originally designed in order to solve concurrency issues can also be used in order to achieve detectability. And finally, we show that detectable implementation with bounded space are possible. So thank you, and I'll be happy to answer any questions.
Thank you. And actually, there was one question for clarification. Is that by Krish? Is that what is a detectable object? So
an object is detectable if after there is a crash, you have a special procedure, a special function that usually we call it recover, and you run it, and when it ends, it tells you whether your crashed operation was linearized, And if it was linearized, it also tells you what is the response of the operation.
Okay. And then the next question by Faith is how does your SPA 2020 paper related to this PODC version?
So in SPA 2020, we presented some scheme in order to implement detectable. It was not for any object, but mostly for a data structure. So how to implement it in an efficient way.
Okay, cool. And then the next and actually final question for the time, for the sake of time. Watch, actually I will unmute you. Your question is longer. Maybe it's easier for you to ask directly. Please go ahead.
Okay, hi, this is Wojciech. I was just curious why the linear lower bound on space does not follow from the assumption that each process uses a private non-volatile structure to remember, among other things, what operation it last invoked. Can this auxiliary or additional data structure itself not be viewed as some form of auxiliary state?
So the lower bound was for the shared number of bits. So technically you can have this auxiliary state passed you as a persistent data, but you can have it private. You don't need to share it among processes. And the lower bound was for the number of bits, shared bits.
Okay, thank you.
Okay, thank you. Let's thank the speaker. And Danny, you are next. So the next talk is by Danny from Ben Gurion. Its title is Long-Lived Snapshot with Polylogarithmic Multi-Step Complexity. And Danny, please share your screen and I just unmute you. Please go ahead.
Hi everyone, can you hear me?
Yes.
Great. Can you also see the presentation?
Yes, it's pretty good.
Excellent. So hi again, this is a joint work with Mizra Hadbeg, Alessia Milani, and Corentin Travers, in which we consider a standard shared memory model where processes communicate via shared memory using atomic read and writes operations, so a classic model. And we consider non-blocking progress conditions that preclude the use of locks, specifically weight freedom, under which every operation must complete in a finite number of its own read-write steps. And as for correctness, we require the standard linearizability condition. And we investigate the well-studied snapshot object whose abstract state is an array with n components. So a single writer snapshot object supports two operations. An update by process I changes the value of the snapshot's i's component. So P2 here can change the value of V2. And a scan operation returns an atomic view, which is a vector consisting of all component values as they have existed at some point in time during the execution of the scan operation. Now, what do we know about the step complexity of implementing snapshots? First, we know that there exists implementation of multi-writer snapshot with linear worst-case step complexity. And as it turns out, we cannot do better in terms of worst-case step complexity because Jayanti, Tan, and Turek proved that for any non-blocking implementation of an object in a large class of objects that include snapshots, there exists an execution in which some operation can be made to perform a linear number of steps. So this seems to settle the problem, but it turns out it does not, because 15 years later, Aspen, Satia, and Sensor Hillel observed that the lower bound holds only for executions which are very long, that is, in which the number of operations applied to the object is exponential in n, the number of processes. And they leverage this observation to construct counters and additional objects for which the worst case step complexity is polylog in the length of the execution. And then by building on these results and extending them, we had a result by Aspen, Satia, Sensor Hillel, and Ellen that presented an implementation of a B-limited use snapshot in which the complexity of operations is polylogarithmic in B, where B is the maximum number of update operations that are supported by the snapshot implementation. However, also this implementation, as the length of the execution grows, operation step complexity grows as well. And when its length becomes exponential in n, step complexity becomes linear in n once again. So the lower bound of gigantic Tan and Turing does not preclude algorithms that have sublinear amortized step complexity, that is average step complexity over all operations in the execution. But all previously known snapshot algorithms had linear amortized step complexity, at least in long executions. So in this work, we present a weight-free single-iter snapshot algorithm that has O of log n cube amortized step complexity in all executions regardless of the length. And this is an exponential improvement in terms of the amortized step complexity in comparison to previous work. We do so by implementing a new two-component max array. So what I'll do next, I will describe what two-component max array is, but before that, let's see a high-level, the high-level construction of the snapshot algorithm of Aspen et al. So it is based on two objects. One of them is the max register, and the other is a two-component max array, which by itself also incorporates a max register. So now I need to explain to you what these two objects are. So a max register stores integer values and supports two operations. The write max operation writes a new value, and the read max operation returns the largest value written by write max that was linearized before it. And in the algorithm they presented, both operation types include log v steps, where v is the value read or written. When the register's value is exponential in n, this complexity can become superlinear. So this is the problem of this max register. It cannot become unbounded with bounded complexity. So in recent work, Beg et al. Presented the first weight-free unbounded max register, which is a max register that can assume any non-negative integer value and has amortized state complexity, which is logarithmic in n, also in log executions. And we use this in our new construction. So the key technical tool developed by Aspen et al. For their snapshot algorithm is the two-component max array. Essentially, this is a two-component snapshot object where each component is a max register rather than a simple register. So we call this component the left and the right components, and the object supports two operations. So max update operations invoke the max update operations invoke the right max operation on either the left or the right component of the array. And the max scan operation simply returns an atomic view of the two components. And when the values of both max component is bounded by m, the worst case step complexity of the max update operation is O of log m, while that of max scan is O of log m squared. So returning to the schematic view of the snapshot implementation by Aspen et al., to obtain a snapshot algorithm with polylog amortized step complexity, we retain the algorithm, but we replace the objects that it uses and their implementation. So first, we replace every max object by the unbounded max register of Beg et al. That has logarithmic amortized step complexity. And second, we replace the two-component max array with a novel implementation of a polylog amortized step complexity max array that has log n square amortized step complexity, and this is our key technical contribution in this work. So plugging in this two-component max array into the snapshot algorithm of Aspen et al. Yields a log n cube amortized step complexity snapshot implementation. So I won't have time to get into the technical details of the implementation. You're welcome to watch the longer presentation and also to read the paper. Thank you.
Thank you, Danny. We have time for maybe one or two questions. Anyone?
So let me see if I can see the chat once again. Yes.
I guess I don't have questions. So maybe I have one more. So like, is there any open problem in this? Like, actually, like, what's the worst complexity? Because like you show the amortized time, right?
Yeah. What's the worst case step complexity?
Yes.
We didn't analyze it. I think it is linear, but we need to analyze it in order to.
I see. Okay. So is there any lower bound on the worst case step complexity?
Yeah, on the worst case step complexity, there is the lower bound by Jayan, Titan, and Tuig. But this lower bound only holds for long executions. If the execution is shorter, then you can do better than that. But on the amortized step complexity, I forgot to mention, there's also a logarithmic lower bound. So there is a gap between this logarithmic lower bound and the log square upper bound.
Okay, sounds good. And we have two more questions. One from Karen. It's like, could space be reused here after a while?
So do the new technique apply to other data structures? We applied a technique that is similar in a sense in our this last year paper in order to construct a polylog amortized step complexity counter. And we were able then to do this also for a snapshot. Is this, I'm not sure this suffices to call it a technique, but that's an interesting question, maybe, I don't know. I'm not sure if you can apply it to other data structures. This has to be checked. And I see there's another question. It seems that you're trading step complexity with space complexity. Well, I think that the space complexity, and I guess Faith can correct me if I'm wrong on this issue. I think the previous implementation of the snapshot also had a long-lived version, which also had unbounded space complexity. So in terms of space complexity, the new implementation also has unbounded space complexity. But is this an inherent trade-off? It's an interesting question. I'm not sure.
Cool. And then there's a one question from Karen. Yeah, actually she typed it before. So could space be reused here after a while?
Yeah, that's an interesting question as well. We actually have another direction in which we can reuse space for implementing such objects using another approach. In the current approach, you only flip values from 0 to 1. You can never, once you flip them to 1, this stays here this way forever. The question is whether you can recycle it later on. I'm not sure, actually.
Okay, so in the interest of time, yeah, let's take the other discussion to offline. Yeah, thanks, Danny. All right, let's go to the next talk. It's by Debian Eames from Marcel, and the title is From Basal Identity to Space Optimal Election in Anonymous Memory System. Okay, Damien, go ahead.
Hello, can you hear me?
Yes, and we can see your slides. Thank you.
Great. So this is a joint work with Emmanuel Godard, Michel Renal, and Gadi Taubenfeld. And this work is about leader election in anonymous memory systems. And we'll see how we use Bezout's identity to solve the problem. So in an anonymous memory system, each process has its own map to access registers. So every process can access the same set of registers, but they index them differently. If we take an adversarial view of this, it means that the adversary shuffles the memory map of each process. Now, this model was used implicitly in the early 80s in a paper by Rabin, but it has been formalized only recently by Gadi Taubenfeld in his PODC paper from 3 years ago. Now, our goal in this work is to obtain tight space bounds for leader election using an anonymous memory. And we also consider two generalizations of leader election, namely de-election, in which up to D leaders can be elected, and exact de-election, in which exactly D leaders must be elected. So in the leader election problem, every process must output the same identity, the identity of the leader. So in the classical, that is non-anonymous memory setting, Steyer and Peterson gave the following results in 1809 in a paper that was published in PODC actually. So with optional participation, the ceiling of log n plus 1 registers are both needed and sufficient, so that's a tight bound. And with mandatory participation, they give an algorithm that solves the problem with 3 registers. And they give a conjecture that says that 3 registers are needed. Well, actually, this conjecture turns out to be false, and we disprove it by solving the problem using a single register. And we then use this algorithm as a building block for our more general anonymous memory algorithm. So our main results are the following. For n processes and m anonymous registers, leader election can be solved if and only if the greatest common divisor of m and n is equal to 1. De-election can be solved if and only if the GCD of mn is less than d. And exact de-election can be solved if and only if the GCD of mn divides d. In order to prove this, we give an algorithm that solves exact de-election and an impossibility proof. Now, Bezout's identity is a famous result from the 18th century. And it states that if we have m and m two positive integers, then we can find u and v such that u times m plus v times n is equal to the GCD of mn. Now, we're interested in another form of this result, that is with u prime and v prime positive, u prime times m is equal to v prime times n plus the GCD of mn. And more generally, if d is a multiple of the GCD of mn, then we can multiply everything and obtain something times m equal something times n plus d. So with m registers, n processes, and d a multiple of the GCD of mn, we have u and v such that u times m equal v times n plus d. So in order to solve exact de-election, we proceed as follows. Each register implements u single register leader elections. So in total, we have u times m elections. Processes compete in these elections, and each process competes until it has won v elections. In this example, 1 election per process. Once every process has won its v elections, there remain d elections, because u times m minus v times n equals d. Now remember that we are in an anonymous memory setting, so this may be the view of one process. Another process may index the registers differently, but the remaining elections will be the same at every process. And these elections will be used to elect the D leaders. So, as a conclusion, we give a single register leader election algorithm that disproves a conjecture from more than 30 years ago that appeared in PODC. We give an algorithm based on Bezout's identity that solves leader election, de-election, and exact de-election, and an impossibility proof that shows that we have tight bounds. Actually, the condition is quite interesting. It's not based on some kind of threshold. It's based on the GCD of M, the size of the memory, and of N, the number of processes. So obviously, if you're interested in the results I presented, especially in the single register algorithm and the impossibility proof, I encourage you to read the paper. Now, there are some other papers that are related that could be of interest. So in our PODC paper from last year, we give tight bounds for mutual exclusion in the same anonymous memory setting. And For some values of m and n, an anonymous memory can actually be de-anonymized and used as a classical shared memory. So we show how to do that, and we give simpler algorithms, simpler than the one I presented today, for some special cases of leader election in our Sirocco paper from last year. Thanks for your attention.
All right, thank you. Very interesting result. Any questions? Okay, question. Yeah, I will actually unmute you since your question is a bit long. Go ahead.
Wait, can you hear me?
Yes.
Okay, I just posed a question here in the chat. If you have a given number of registers, a given number of processes, and the problem to solve, can you then sort of add dummy processes to make it, and in case the condition would not hold, right? Can you add dummy elements of some form easily? Can you just like pretend they're processes, or do they have to something to do?
You actually cannot add dummy processes because they have to participate. Yeah. So processes have to include their identity. They have to acknowledge the leaders. And so you can't really use dummy additional identities.
Okay, thanks.
Thank you. Any other questions? If not, actually, I have one. So that this non-threshold based impossibility or type result is very interesting, but I'm curious about for your impossibility proof, how do you, I don't know, construct it, or how do you prove it?
So basically we construct an execution in which we have groups of processes such that the indexing of the memory is organized along a ring. So groups start some values apart, and they follow the same cyclic order. And we then run the processes in lockstep, and we show that the symmetry cannot be broken in this way, because the processes always stay the same distance apart when they apply operations to the registers.
I see. Okay, interesting. Cool. Any other questions? Okay. Actually, there's one more question. Can you see in the chat? Oh, actually, let me unmute you, Kelly. Okay, please go ahead.
Oh, this is just based on Christian's previous question. I'm not sure if I misunderstood the answer, but why isn't it the case that a process can just simulate multiple processes? You said that they have to like have their own unique ID, but like, does it have to be authentic? Can they be Byzantine? Can they be lying about their process?
Well, actually, the thing is, in order for the problem not to be trivial, the processes need to have the same code, and they can't have an ID embedded in the code, right? So if you had a process, well, I'll complete my answer from earlier, which was a bit short. So if a process wants to simulate other processes, then every process in the system has to do the exact same thing, because the codes are exactly the same at each process. The only difference is the identity. And so if a process simulates multiple processes, then all the processes simulate multiple processes. So what you can do is multiply the number of processes in the system by adding dummy ones, but you can't just add one or two. A process may simulate, say, 3 processes, but then every other process in the system also has to simulate 3 processes. Is that clear?
Yes. Okay. Sounds good. And yeah, let's bring the other discussion offline, and then let's move on to the, yeah, thank you, Damien. And let's move on to the next talk. It's a brief announcement and presented by Jennifer Welch. It's called Store Collect in the Presence of a Continuous Churn with Application to Snapshots and Lattice Agreement. Jennifer, yeah, I just unmute you. Please share your screen.
Okay, so I'm here to promote the store collect object as a useful primitive in systems that experience ongoing churn. This is joint work with Hagit Atiyah, Sweta Kumari, and Archit Samani. We're considering distributed systems in which nodes can continually enter and leave, a behavior that we call churn. When they're in the system, the nodes communicate via asynchronous message passing and are subject to crash failures. This model is motivated by peer-to-peer mobile and sensor networks. The key feature is that the churn never stops, although the rate of churn is always bounded. Programming in such a churn-prone system is tricky, as you have to keep track of who is in the system and deal with low-level message passing. By analogy with techniques used in static systems, we'd like to encapsulate the messiness with some kind of shared objects. Now programmers can use familiar data structures and not worry about tracking the system composition. But which object should we try to provide? We propose the store collect object as a strong candidate, which was first introduced by Atiyah et al. Each node can store a value and collect a set of recently stored values. So in this diagram here, you'll see that nodes P and Q are performing some stores. The collect invoked by node R must return for each node a value from the most recent preceding store or from an overlapping store. The collect by node S is subject to the same constraints. Notice that this example is not linearizable since R sees P's old value and Q's new value, while S sees P's new value and Q's old value. And this collect by node T must return a value for each node that is at least as recent as that returned by any preceding collect. Store collect is similar to an atomic snapshot object, but it's weaker since the atomic snapshot operations must be linearizable. We've designed a simple and efficient implementation of a shared store collect object that hides the complexity of the churn and the crash failures. On top of this object, we show how to implement a suite of useful data structures, including max registers, abort flags, sets, and atomic snapshots. Our atomic snapshot algorithm is also simple and efficient, although proving its correctness requires the right approach. Atomic snapshots can be used to solve many problems, such as group membership, mutual exclusion, and more. In our paper, we show how it is trivial to implement a generalized lattice agreement object using an atomic snapshot, which in turn is known to be useful in implementing other objects, notably conflict-free replicated data types. All the brown boxes indicate algorithms that are given in our paper, and all of these implementations inherit the churn resilience and fault tolerance from our store collect object. And here is a link to our full paper. Thank you.
Thank you. Any questions? Anyone? So, okay, maybe let me ask a question. So like Jennifer, I know that you also have like this like Byzantine churn tolerant like register. Does the technique apply to this store collecting, or like the Byzantine version is not that straightforward?
Yeah, so that's a good question. Hadn't really thought about that. So we did have to make some changes for the register situation, going from crash failures to Byzantine failures. I would think that we may be able to do the same thing, but again, as somebody else said, the details would have to be worked out. So Edith has a question. Is the set of registers, oh, do you want to just ask it, Edith, or I can read it? Is there time? Maybe there's no time.
Yeah, let me unmute Edith. I just unmute you.
Yeah. Hi, Jennifer. Thank you.
Sure.
I was just wondering what is dynamic. So the registers are bound in some way to the dynamic set of participants, or is it just a static set of registers that are implemented by a dynamic set of?
No, so basically, I guess it wasn't very clear in the picture, but the idea is that as the nodes enter the system, then their value, so their ID value are part of the set, and then that can change. Yeah, so basically, as Hagit says here, the object exports a set of one register per participating node.
Okay, Thank you, Jennifer. Yeah, in the interest of time, let's move on to the next brief announcement. Presented by Faith. It's called Why Extension-Based Proof Fail. And Faith, please share your screen. I will unmute you right now. All right, please go ahead. We can see the slides.
Okay, this brief announcement is about extension-based proofs and their limitations. And this is joint work with Dan Alistar, Jim Aspinus, Ruddy Galavishi, and Lucky Zhu. It's well known that there's no weight-free algorithm for solving consensus in asynchronous shared memory systems where processes communicate using registers. This proof uses a valency argument. Many years later, the same impossibility result was finally proved for a k-set agreement, where up to k different values can be decided. However, the proofs are much more complicated and all use some form of arguments from combinatorial topology. An actual question is whether there are simpler proofs of this result. We formalized this question by defining the class of extension-based proofs which contain valency arguments. Then we proved that there is no extension-based proof of the impossibility of k-set agreement when k is at least 2. An extension-based proof is a game between a prover and an algorithm, which the prover is trying to show is incorrect. The prover repeatedly asks questions and the algorithm responds to them. The prover's queries can be chosen adaptively based on the responses it gets from the algorithm. Initially, the prover only knows the initial configurations of the algorithm. The prover may repeatedly query the algorithm by choosing a configuration it knows in a process P that hasn't yet halted in C. And the algorithm responds with what happens when P takes one step starting from the configuration C. In particular, it gives the new value of the object P accessed, P's new state, and what value P outputs if it outputs a value in its new state. The prover wins by showing that the algorithm is incorrect. One way the prover wins is if the algorithm violates agreement or validity. A chain of queries is a sequence of queries with the configuration results from one query. The configuration resulting from one query is the input configuration to the next query in the sequence. Another way the prover can win is if the algorithm allows it to continue a chain of queries indefinitely, violating weight freedom. For an output query, the prover chooses a configuration C that it knows, a set of processes P, and a possible output value Y. The algorithm can respond with a finite sequence of steps by processes in P, such that starting from configuration C, one of them outputs the value Y. Alternatively, the algorithm can say that no such sequence exists. After making finitely many output queries and chains of queries without winning, the prover must choose a configuration C it knows and start another phase. In the second phase, the only difference is the prover can only ask queries about configurations that are reachable from C. This keeps on happening until the prover cannot start a new phase, because all the processes of output values are terminated in the configuration it chose. In this case, the prover loses. However, if the prover can continue for an infinite number of phases, it wins. In our Stock 2018 paper, we proved that there's no extension-based proof of the impossibility of k-set agreement among more than k processes in the non-uniform iterated immediate snapshot model. Since then, we've proved the same result in the non-uniform iterated snapshot model, i.e. not immediate snapshot. Both of these models are computationally equivalent to the asynchronous shared memory model, where processes communicate by reading from and writing to shared registers, in the sense that any task that can be solved by weight-free algorithm in one of these models can be solved by weight-free algorithm in the other two. The NIS model was a good model to work with first because algorithms in this model have nice representations using combinatorial topology. The proof for the NIS model is simpler, but you don't need any topology to understand it. One of the main differences is instead of considering simplicial complexes, we consider unions of n-vertex cliques. To prove that k-set agreement is unsolvable using an extension-based proof, a prover must win against every algorithm. To show that there is no extension-based proof, for every prover, we adaptively construct an algorithm based on what the prover does, and show that the prover loses against this partially specified adversarial algorithm. Thank you for watching, and I'm happy to answer any questions.
All right, thank you, Faith. Any questions? Okay, Baldi, let me unmute you. Please go ahead.
So Faith, if I'm given the impossibility result for k-set agreement as a black box, starting from there, can I always prove things using extension-based proofs? That is, you can.
No, not necessarily. I mean, are you saying that can you use reductions? Is that what you're asking?
I'm saying, is it the case that extension-based proof always wins together with the K-set agreement proof as given to us?
I'm not.
If I can base my proof on K-set agreement, so I already know the K-set agreement impossibility result.
Right.
Now I want to prove something else.
Right.
Can I always do extension-based proofs using the K-set agreement as a lemma somewhere?
Not that I know of. I mean, it would depend on how you actually want to use K-set, the proof of impossibility of K-set agreement. I mean, there should be. It would depend on the problem, and even if you had a reduction relating to K-set agreement, it's not clear that it would carry over to extension-based proofs.
Okay, maybe yeah, let's bring the discussion offline since we are a bit off time. And thank you, Faye. And let's next presentation. Sorry, anyone? No? Okay, cool. The next presentation is by Stefan, and the title is the only undoable CRDTs are counters, and it's from OKMO Lab. Stefan, please go ahead. Actually, I have to unmute you, sorry. Let's see. All right, I just unmute you, thank you.
Thank you.
Cool. And actually, we cannot see your, oh, okay, now we can see the slide.
Can you see? Okay, so I'd like to present this result. I'm going to be talking about CRDTs, or conflict-free replicated data types. The way that these work is that they allow you to synchronize a data structure across multiple machines in a network. They work by having each replica keep a log of the operations that have been performed. And then when it comes time to synchronize the different replicas, they exchange the logs of operations they have performed and apply those operations to their own state. To guarantee that this does actually synchronize, that we end up in the same final state, we need to know that operations that happen in parallel are commutative, that they will result in the same state no matter which order they're applied in. This is the operation-based viewpoint of CRDTs. There's an alternative presentation of them called based on states and merging, but this is the one I'll be talking about today. An example of CRDTs that I'd like to discuss is the OR set, which is a CRDT that represents a set to which things can be added and removed. It's represented as two sets, one set of all the things that have been added and another of all of the things that have been removed. And each thing that has been added has an ID, so that a thing can be added twice with multiple IDs. Both of those sets are only allowed to grow, and an item is considered present if it's been added but not removed. So this is a fairly standard CRDT. It's been reasonably widely used, but it has an interesting anomaly that I'd like to discuss today. So the example I'm going to use is Alice and Bob, who have a shared to-do list, which they're representing as an OR set. They have two things on the to-do list. They want to prove the theorem and write the paper. So Alice proves the theorem, crosses that off, but then realizes that there's a bug, and so she re-adds prove theorem to the to-do list. So this doesn't change the state. She's removed it and then re-added it. When she re-added it, she had to add it with a different ID because prove theorem with ID 0 was already in the removed set. So adding it with the same ID would not have, it would have remained absent. So she adds it with a fresh ID 1. But then suppose in parallel, Bob also decides he's proved the theorem and removes it. After they synchronize, they will apply each other's operations. And the resulting state will be that prove theorem appears on the to-do list. ID 0 has been removed by both sides, but ID 1 has been added by Alice and never removed. There are no instances of remove with ID 1, so it should be on the list. The anomaly I'd like to discuss here is that if Alice had done nothing at all, if she had neither removed nor re-added it, then it would not be present. The only action would have been Bob's removal of it, which is a little bit odd. Removing and re-adding has had side effects and changed the state. So in an OR state, although you can use a remove to undo a prior add, an add does not undo a prior remove. If we remove and then re-add, there are some side effects that persist across sinks with other replicas. So the question is, which CRDTs actually have this undoable property? Can all of their actions can be undone without leaving side effects leaking across the state? There are a couple of examples. Counters with plus and minus 1 can be undone. Counters which wrap around, or tuples of a collection of counters. All of these can have an action of increment, which can be undone. And the result I'm going to present today is that this is the complete list. There are no other undoable CRDTs, and every undoable CRDT is isomorphic to one of these. In general, this means that every CRDT either is made of counters, and in particular can be driven to negative states where an action must be performed, something must be added to the to-do list for it to become empty, or like OR sets, there are some operations that cannot be undone. So the full proof is on arXiv. It's the whole paper there is 4 pages long. It's a reduction to a classical theorem of group theory, so there's not a huge amount of, it shouldn't take too long to read. So other than that, I'm happy to take questions.
Thank you, Stefan. Any questions? If there's no question, I have one question. So like, okay. So can you like briefly describe how do you prove this like only thing? Like, can you show that all the other type of CRDT can be implemented somehow to support this undo function?
Yes, so the proof is if you have a CRDT where every operation is undoable, each operation must commute with other ones that can be done in parallel by the definition of a CRDT, then you end up with the actions that can be performed forming a group. The group has inverses because you can undo an action. It's abelian because all of the actions have to commute. And it's finitely generated because in any state, there are only finitely many options that a user can do, which is equivalent to having a bound on the maximum length of any single operation. So the CRDT, all CRDTs which are undoable have the structure of a finitely generated abelian group. And those were classified at the turn of the 20th century. They are only products of cyclic groups.
I see. Okay, that's pretty interesting. And thank you all. That's the end of this section. And I think sorry we run out of time. So I guess the next session will start in 7 minutes. And please take a break. Thank you.
Lewis.
Hello?
Yeah. Should I stop the recording?
Yes, I think so. Yeah, thank you.
Mm-hmm.